Hi and welcome to our talk about our paper Part-of-Speech Tagging of Swedish Texts in the Neural Era. My name is Yvonne Adesam and I'm presenting together with my colleague Sasha Berdzewskis, and we're both from Språkbanken Text at the University of Gothenburg. Our paper deals with part-of-speech tagging of Swedish texts, and we plan to, or have reevaluated part-of-speech tagging for Swedish. So the previous standard for tagging has been using the Hunpos tagger trained by Bea Megiesi on the Stockholm-Umeå corpus. And this, of course, was a while ago, so as we all know, the NLP landscape has changed quite a bit in the last decade. The reason for us exploring part-of-speech taggers for Swedish is that we at Språkbanken Text have a number of tools for language technology and linguistic research. And the main tool is Corp, which is used for searching and exploring large-scale corpora. And as you can see, we have at least 13 billion tokens of modern Swedish text, and there are also historical data as well. And then we have our annotation pipeline Sparv, which you can use for annotating text. So the main point here is that we want to find a tool which has high accuracy and is fast enough to be used for large amounts of Swedish texts.
When selecting taggers to experiment with, we paid attention to quite various criteria. First of all, we wanted them to use different methods, and we took both neural and what we call pre-neural taggers. Then we wanted them all to be or have been at some point very good, state of the art or so, to be open source, and to be easy to integrate in Sparv, since that's our final goal. And that's a merely practical consideration, but it actually plays an important role. Keep in mind that our research question is not only what is best, but also how much. So we expect modern neural taggers to be better than older ones. But how much the difference is it worth the gain? And also in what way, since we will do quite detailed error analysis, we will be able to see where the differences lie. And so the taggers that we use are as follows. BERT model, trained by National Library of Sweden, called BERT. Flare, and yes, and BERT is made available via Hugging Face, which so the tool that we are actually using. Flare, modern neural framework, which makes active use of both classic embeddings, word-to-vec, and token embeddings or dynamic embeddings, contextualized embeddings. We tried different ones, but it works best with their own, so-called Flare embeddings. Stanza, a pipeline from Stanford University, which also makes use of classic embeddings. Marmot, a somewhat older conditional random field tagger, which makes it possible to plug in a morphological dictionary, which we do. And even older Hunpos, open source re-implementation of the classical TNT tagger from 2000. And note that all of them make some use of additional data, and that actually will be crucial for their success. So we'll say a couple of words about that later.
So next we present our corpora. We use 3 tree banks, Talbanken SPX, Talbanken UD, and Eucalyptus. And all 3 of these are roughly of equal size, about 100,000 tokens. And that's also a reason for not using SUC, the Stockholm-Umeå corpus, since this is a lot larger with 1 million tokens. Each of these 3 corpora or tree banks use different tag sets. So Talbanken SBS has the Stockholm-Umeå corpus tag set. Talbanken UD is part of the Swedish UD tree bank, and then we have Eucalyptus, which has a newly developed tag set, and which is sort of most in line with the modern view of Swedish syntax. And these three also contain multiple different genres. In particular, Eucalyptus has 5 different types of texts, one of which is blogs. So what we did was we divided them into trained test sets based on, for Eucalyptus, based on the different text types. And that's the reason for doing 5-fold cross-validation for all the 3 corpora. And when we sampled train test data for the other 2 resources, we used consecutive splitting to make sure that we have the same text in as few different splits as possible. Generally, our results show that the BERT tagger does the best, while Hunpos does the worst, which is maybe not so surprising considering the age of Hunpos and also the use of extra material for the other more modern taggers. So the BERT tagger is somewhere around 96.6 to 97.7 in accuracy, while Hunpos lies around 91 to 93%. As you can see, Eucalyptus has the worst results, and they also have a higher standard variation, which is the number in parentheses. And we wanted to explore if this is because of annotation inconsistencies or if it's more a question of differences between the texts. So what we did was to do a randomized train test division for all 3 corpora. And this showed that Eucalyptus gets more similar results to the other two banks. And also the standard deviation goes down a lot. So just a quick look at training speeds. Hunpos and Marmot are the fastest taggers, where training takes a few seconds, while Stanza and Flare are the slowest, where training takes hours. Interestingly enough, the BERT implementation is quite fast considering the type of tagger it is, with about 3 minutes of training. So it's very well usable for our purpose. A few words about difficult categories considering manual evaluation. So we found that interjections, foreign words, and proper nouns were quite difficult to get right. And of course, these have a high type count. There are few morphological clues for these categories, and they also have varying syntactic functions. In particular, foreign words can appear as almost anything. What we also found was that different taggers find different categories difficult. And this is something that we can exploit in, for example, an ensemble method. And finally, we also find a number of inconsistent annotation, which is sort of behind some of these difficult categories. You will find more examples of this in the paper.
Yvonne already mentioned some of the factors that seem to affect which tags are more difficult, but we wanted also to apply a more rigorous statistical approach to explore the same question. And as far as I know, this is something that's not often done in the NLP, while it's quite interesting. So we try for every tagger on every tag set to predict the accuracy that a given tag will have using the following factors. Frequency of the tag, the idea is that more frequent tags will be easier to guess. Type token ratio, TTR, of tokens that have this tag, and high TTR is supposed to make tag more difficult, and it's sort of different words instead of one word all over again. Average difficulty of tokens that have this tag. This is a more complicated idea. So basically, it's a measure of unidirected association from token to tag. If we know the token, how difficult it is to guess the tag. If we take the word whose, house, then it's difficult to know whether it's singular or plural, since they are systematically ambiguous. And then the conditional entropy of the tag will be high. And then we take average entropy of all the tokens with this tag and use this as a predictor. And then we do the same for token endings and end words, which contain most of the inflectional information. And ending here is the last two symbols. It would have been much better with real grammatical ending, but we would need morphemic annotation for that. So we fit 15 different models, and here are the average results. The first column is the actual effect. The second column shows how often the predictor is significant. Models have on average very high goodness of fit, so they fit the data quite well. And as you can see, TTR and tag by token entropy have results as we expected, so they are both negative, TTR very strongly so. Frequency has a positive effect, again, as expected. But tag by ending entropy has a reverse effect, so it's not so strong and it's not always significant, but still it's positive. And that's something we cannot explain, why ambiguous endings make tags more easy. So it must be a correlate of something else, but we do not know why. One last thing to say is that we tried ensembling methods, which is natural given that we have 5 different taggers. We tried simple voting and naive Bayes, and voting doesn't work. Bayes gives some small improvement, which is not significant. By the way, we didn't say, but all other differences that we observed that we briefly reported before were very much significant. This one is not. So the ceiling is not reached. There is some room for improvement, and maybe more sophisticated ensembling methods could do better. To conclude, we observe differences in quality between all 5 taggers. Actually, each pair is significant. And neural taggers are on average much better than pre-neural ones. And embeddings seem to be the key to success. What kind of embeddings you use and what they are trained on is important. We think that BERT is so good, at least also because of its trained on a huge corpus of Swedish and quite well-balanced corpus. Speed, neural are much slower. QBERT is a pleasant exception. It's fast enough to use in practical applications, at least on GPU. There are no major differences between text sets that would be easy to summarize in a couple of sentences, but if you look closely, then there are some interesting things in the confusion matrices. And again, manual error analysis is somewhat difficult to summarize, but most general level of abstraction, high TTR is causing problems, words that have varying syntactic functions are causing problems, systematic ambiguity like whose singular or plural are causing problems, and fuzzy boundaries between categories. For instance, some of the text sets have distinction between verb and auxiliary, which seems to be difficult also for annotators. It's conceptually difficult, and then it's difficult for taggers as well. And statistical error analysis basically confirms some of these observations and yields also one unexpected observation that we cannot fully explain away. Ensembling did not really give a significant improvement, but ceiling is not reached, so maybe there is some hope for that. And that's what we wanted to tell you about tagging of Swedish texts in year 2021. Thanks for your attention.